Wow, good crowd tonight. I hope everybody's having a good visit. Thank you for coming again. It is time for Microsoft Update 2. No, I'm for the McKinney Amateur Radio Club meeting. All right, guys, it's time. It's time for our presentation. We're going to let Larry do the intro of our presenter. Here you go, sir.
Thank you very much. Thank y'all for coming. You might have noticed the last few weeks, few days, we've had some occurrences up in the upper atmosphere. The sun's been kind of giving us a little bit of messages back and forth. Some activity. Can you hear me now? I'm sorry. And the sun's been giving us some activity. Well, just so happens we have a man here tonight completely, utterly qualified to give us a discussion on this topic. And not only that, he's a ham. Alpha Delta Zero India uniform. And may I introduce Dr. Rob Steenberg. And I've got a laundry list here of his qualifications, but I will tell you, quite a guy. He's been a space scientist at SWPC since 2014, worked with NASA, North Carolina State University. He's got quite a pedigree here. But please put your hands together and welcome Dr. Rob. Thank you for coming.
All right. Well, thanks for having me. Just a small clarification. I'm a Mr. Rob, not a doctor yet. Been working on it, but it's been a long road. My hope is to finish before I'm in my 80s. But until then, I did do a master's in applied physics at the Air Force Institute of Technology. But in any case, yeah, I'm here today to tell you about what's been going on with the sun. And I'm going to try and share, make sure you can see. So hopefully you're seeing the slide presentation now. But yeah, I appreciate you guys having me out here. I've done quite a few of these, and you are going to be the recipients of the most exciting space weather activity discussion. We just had the biggest geomagnetic storm we've had in 21 years over the weekend. So it was pretty spectacular. And so we'll take a look at a little bit about that. And I'll talk about how you can use space weather as an amateur radio operator to your advantage. That has a song, but we don't need the song. I just want to show you the video. So this is an animation that starts from solar minimum and basically shows you the development of sunspot regions after we go through solar minimum. So we're still kind of languishing in solar minimum there, and I'm going to speed this up because otherwise we'll sit here for 5 minutes and watch this thing spin. But you can see during solar minimum, obviously, not a lot of sunspot activity. It's pretty quiet. Your F10.7 solar flux goes way down. It's tough to communicate on the higher bands, higher frequencies. So you got to make good use of 40 meters. But as you can see, as we entered 2021, we started ramping up. And I'll just jump ahead here a little bit so you can see there's a lot more activity now. And you can see both in the northern and southern hemisphere, those sunspot regions. The sun rotates, as you can see here, from left to right. It does a complete rotation every 27 days on average. The equator rotates faster than the poles. And that's what gives rise to some of this activity that we see. But you can see we were seriously climbing up there in activity. So this has been a more pronounced cycle than the last cycle we had, which was cycle 24. We had some big events in September of 2019 or 2017, but nothing like what we've been seeing lately. So this is pretty pretty awesome. Yeah, and you can see this one ends, I forget how far out we go into April 2023. So it's even bigger now. There we go. So here's the progression. The current cycle's outperforming the initial consensus prediction. So every solar minimum, a group of scientists come together and from all around the world, actually, and try and make a prediction for the next solar cycle. And there's a variety of techniques that go into this. But like any forecast by committee, it has its issues. The initial forecast was shown in red here. And you can see right away, we just took off very quickly above it. And that trend has continued. So we're outperforming. But one of the things we're trying to determine now is, okay, when is this thing going to peak? Are we in the peak now? The problem with the solar cycle is you don't know until you have passed the peak of the solar cycle. And then things just keep going down. You're like, well, it doesn't look like it's going to get any bigger. But you can see the last cycle had two distinct maxima. One was bigger than the other. And that is the difference between this northern and southern hemispheres. So sometimes you'll see two peaks associated with peaks in both hemispheres. So we've got an updated plot, but I can't publish it yet. But they did update the forecast. Maximum sunspot number up to around 173 with a peak sometime between January and October of this year, which is a pretty long span of almost a year. But max 10.7 flux, this monthly smooth value of 194, but we've already been, on a daily basis at least, we've been above that. Here's another prediction from a gentleman named Scott McIntosh, who is also here in Boulder, Colorado, at the High Altitude Observatory, and his was much more aggressive. And what we found is it's kind of living in between the consensus prediction and his prediction. This map just shows you a series of solar cycles. The one on the bottom goes back to 1980, and all this is displaying is in the bottom image, the transition of the poles. So every 11 years, each solar cycle, the poles flip. So for instance, in cycle 23, we had negative polarities in the north part of the sun and positive polarities in the south, and it flips over in the next cycle, 24. And then it's in the process of flipping again. And what's happening here is you can see these areas on either side of the sun's equator where the sunspots are forming in the higher latitude at the beginning of the cycle. And then as time wears on, they migrate closer and closer to the equator. And then you enter solar minimum. And then the process starts again. And we're still working on figuring out how this happens. There have been some different theories that have been tested, and unfortunately, our attempts to model them so far have not been very successful. So, what gives our star space weather? 3 ingredients, really: magnetism, convection, and differential rotation. So I talked about the 27-day rotation, faster at the equator. So what happens? You have magnetism that's produced deep in the sun's core that rises up through convection, just like you could think of thunderstorms. But that gets pushed up and outward. It breaks through the solar surface and shows up as sunspots. And then these fields get twisted around. And then on the bottom, these are called magnetograms. And the black is showing you negative areas of polarity and white is positive. And you can see how they grow and get mangled up. And this gives rise to solar flares and another phenomenon called coronal mass ejections, which we've been seeing a lot of lately. So here's the region that's given us all the activity over the past week or so. This is region 3664. And what I'm going to show you here is a combination of white light imagery, which is what you'd see if you had your eclipse glasses and you were looking at the sun, because this sunspot was actually big enough to see without any magnification. So you can see it developing. You can see the flux and magnetic fields emerging. And look how mangled up it gets and how big it gets. So this wasn't bigger than the spots we had last cycle. We had some big ones last cycle as well. Actually, a couple that were larger, but they didn't do nearly as much as this one did. This was a overachiever in a lot of ways. But the general principle for space weather forecasting is the larger these things get and the more complex they get magnetically, the more likely you are to have a solar flare or other eruptive event. And so this is the kind of stuff we look at every day at the Space Weather Prediction Center when we're trying to make our forecast for the next 3 days. Let's see if I can get to the next slide. There we go. Now, this is awesome. This is in extreme ultraviolet. This is from a spacecraft called the Solar Dynamics Observatory. It's flown by NASA. It's been up there over a decade, I believe now. But it produces some spectacular imagery. This is the best imagery that we'd ever seen up until that time from a space-based platform. And the level of detail is just incredible. So, this guy. So you can see the flare activity going on there. Those are the bright flashes that you see. And in some cases, you have material that's actually erupting from the surface. That giant bounce you saw of the sun is the explosive nature. No, it's not. It was an instrument issue, but this thing can really get going. So this is just beautiful to watch, and it's hypnotic. But you've got all sorts of entangled magnetic fields there that are holding the plasma aloft and twisting. You break the magnetic fields, and then they reconnect, and that violent reconnection is what gives rise to the flare, which emits energy across all wavelengths of the electromagnetic spectrum, including white light and radio signals as well. So we can actually use some properties and characteristics of the radio signals from the sun to determine whether or not we have any eruption occurring and sending a big ball of plasma our way. All right, and then this is the image of the coronal mass ejections, or CMEs, that happen. So this is where part of the sun's atmosphere actually gets blown off forcefully. And they can be moving anywhere from 400 to over 2,000 kilometers per second. So that's fast on the high. Well, it's fast on the low end, but in the relative to the work we do, when they start approaching 1,000, it starts getting really interesting. And the CMEs, or coronal mass ejections, that we had during this past week were some of the fastest I'd seen in a while. I don't think there are some estimates that put them up around 1,500 to 1,800 kilometers per second, but most of the ones that we modeled fell around 900 to 1,000 kilometers per second. So there's one. There's another one. There we go. That's the barrage. So that's kind of like machine gun fire from the sun. And if you keep an eye on the very center while this is going on, that's the region there in the southern hemisphere that's given all this activity. So you can see right there where it's center disk and pointed right at Earth, we just got a sequence of eruptions. And that last one there, I can talk a little more about that. We counted at least 7 before the big storm hit. All right, let's see. Go back here. All right. Oops. Trying to get you to the last frame there, because that shows you another aspect of space weather. All right, I guess it's not going to let me stop there. But in any case, at the very end, all those speckles that you see are actually charged particles, protons and heavy ions, hitting the detector in the actual spacecraft. What we've got is a artificial eclipse, and you can see this is called the pylon, coming in from the lower left, and that black area is where it's blotted out the brightest part of the sun, allowing us to see the sun's corona, and hence the name coronal mass ejections, or CMEs. I also like to call them big blobs of plasma, or in some cases, interplanetary projectile vomit from the sun. It's a vivid way of imagining it, but that's not too far off. All right, let's go to the next one. All right, this is the next step in the process. So we're monitoring the sun. We watch that region grow. We assign probabilities of flaring to that region based on its size and magnetic complexity and its climatology. What's the history of those types of regions? Because we have a whole way of classifying them. And based on what we classify it as, will tell us the potential for flares. And this one had a lot of potential. After we do that, we monitor it and we look for those CMEs. When those happen, we have a tool that allows us to, based on the images, we look at subsequent images, determine the speed, the direction, how wide it is, and its origin. And from that, we can plug that into a numerical space weather prediction model you see here called WSA-NLIL. And this is looking, if you were looking down at the north pole of the sun in the ecliptic here, that green spot is Earth. Check this out. 1, 2, 3, 4. There are a couple mixed in there. There's a couple more at the end. But, and what happens is that first one kind of clears the path for the ones behind it, so they don't have as much. And you can see them merging here. And so there was a lot of merging going on. And that just made a big mangled magnetic mess by the time it got to Earth. And the magnetic field in that CME will attach itself to Earth's magnetic field, depending on how it's oriented. If it's oriented correctly, like you play with refrigerator magnets and stick them together, if it sticks really well, that's going to transfer a lot of energy into our atmosphere with a lot of consequences. This is just a timeline that shows you all of the flare activity in the top row. This is taken from our GOES spacecraft, which is the same satellite that provides you images of clouds that you see on your local news broadcast on the weather segment. But it also has space weather instruments on it, including one that measures X-rays. And this is how we classify the flares, is their X-ray output. And you can see all these peaks here. The strongest flares are called X flares. We had the strongest one of the solar cycle so far today, which was an X 8.7. They've measured flares over X20. So this is by no means a monster flare, but it was the biggest in the cycle so far. In the second row here, what you see is GOES proton flux. So here we are tracking protons at 10 mega electron volts, 50 and 100. And the higher the energy measured in MeVs, basically the more potent and faster these things are, and the deeper they can penetrate. Above 30 MeVs, particles can penetrate spacesuits of the astronauts who are outside doing extravehicular activities or spacewalks. So they're concerned about those hundreds, and it runs all the way up into 500 MeV protons, all the way up to giga electron volts. So there can be some pretty potent particles out there. So we see an event that was associated with this X flare. You can see GOES is located at geosynchronous orbit, so it made its way from the sun to geosynchronous orbit. It typically does that over the course of hours, although you can have a very rapid event like you see here associated with this X5.8. Notice how we were just kind of cruising along, and then with the hundreds and the 50s, and then all of a sudden it just shot up and then declined again. We had another event, but this was a very slow event that occurred between the 13th and 14th. So I actually worked an overnight shift last night, so I'm still recovering from that. But this third row shows you the magnetic field in interplanetary space, so pretty quiet. This is where the CME hits a satellite that's about 1 million miles from Earth. And because the CME carries a magnetic field, you can see all the crazy ups and downs. And it's these red excursions into the negative territory of what drive the atmosphere to geomagnetic storm levels that in this case reached the extreme or the highest level of geomagnetic storm. And then you can see things kind of settle down. We got another little impact here and here, but then things quieted down. And right now we're expecting a lull in activity, although we have new regions showing up on the left side of the sun that in about a week will be aimed right at Earth. So we'll have to keep an eye on those. This is the wind speed. You can see when the shock arrives at the satellite 1 million miles away. We've actually got two out there. One's called ACE and one's called Discover. The wind shoots up from 500 kilometers per second and it eventually almost reaches 1,000 before it starts settling back down. And then finally, these are the what's called the KP index. This is a planetary geomagnetic index that tells you about how agitated the atmosphere, the magnetic field of Earth is. And so you can see we rapidly rose up into the highest categories right here and had several periods of that before the CME passed Earth. And we finally settled back down till the next shock, but that was not a big one, so we didn't get much out of that. That's what the D region absorption product. So this is of interest to amateur radio operators. This is the highest frequency affected by 1 dB absorption. The proton events will give you issues over the poles, and that's what you're seeing at the top and bottom. Now, that's combined with the sunlit side of the Earth being hit by a solar flare. The bigger the flare, the more absorption there's going to be, and the higher the frequency affected there's going to be. So you can see this went and just kind of pegged it at 35 megahertz. So for HF communications, this is bad news for a while in those areas. Here we're sitting in the night sector, but I've never seen one like this. And actually, somebody on QRZ actually pulled this down. And I thought it was a great example because you don't typically see a pattern like this. It was pretty wild. You can see some pretty significant absorption there all the way up through 15 and 20 megahertz. Now, there are ways to measure the magnitude of a storm. And one of the ways is through something called a DST index, or disturbance storm time. And that is based on the creation of something called the ring current. When we have these CMEs impact us, the ring current is at the equator. So they have a series of stations at the equator that measures the magnetic deviations from what a normal day looks like. And what you're seeing here is this thing plunge for the one we just had down to about 412, negative 412 nanoteslas. So nanotesla, just to measure the magnetic field. You can see, this is a pretty abrupt dip. And so we had a decent storm, and those geomagnetic storms, once they spin up like that, they'll shove the aurora in the northern hemisphere further south towards the equator. And you'll get aurora reports from places like Texas and Florida, Mexico. We've seen events in the past where it's been driven down to Cuba, and those are very big events. In 2003, we had another storm that was similar. It got close to 400, but notice there were two separate impacts here. So that was a prolonged period of pain for a few people. So that's what I talked about here. We reached minus 412 in 2003. We reached minus 383 in the 1989 storm, which resulted in a blackout in Quebec. We got down to negative 589. And in 1921, actually, there was a storm that brought us all the way down to negative 907, plus or minus 132 nanoteslas. And then finally, for the Carrington event, if you've heard of that, a huge magnetic storm that happened in 1859, named for the astronomer that witnessed the flare. The estimates, because we didn't have the type of equipment to record it that we do now, and most of the equipment at the time just pegged and stayed pegged for a long time. But they found one magnetometer that had been modified so it wouldn't do that. And they estimate, based on that magnetometer reading, that the DST would be anywhere between negative 850 to negative 1750. Now, there was one in 2012, a CME, but it was not directed at Earth, but it did hit a NASA satellite called Stereo. And that satellite was made to collect space weather data, which was awesome. And so they estimated the DST from that event would have been around minus 1,200. And we narrowly avoided that thing. It was about 3 days to a week, rotated off the right side of the sun and pointed elsewhere. Because if that had hit us, that had been a really exciting period. I got some pictures actually from Texas, so I figured I'd include them. This came from the meteorologist in charge of the Center Weather Service Unit, which is a meteorological support for the air route traffic control centers. And he went out and took a couple pictures, and it's gorgeous. And we, from my backyard, even though I have a lot of light pollution and I'm surrounded by trees, we had similar kind of purple colors. How we do our job, it starts with an analysis of the sun. So you can see a lot of different solar features that we analyze here. We look for the sunspots. We look for things like coronal holes, which are in some imagery, they appear as big dark areas. And that's where high-speed solar wind is escaping from the solar atmosphere that's higher than the normal solar wind that escapes. So we keep an eye out for those because those can shake up our magnetic field, but at very low levels. We look for neutral lines because that separates the positive and negative polarities, and the more mangled up those neutral lines get, the bigger the chance for flares. We look at plage, which is the region that appears white if you're looking at it in a hydrogen alpha image, which is one of the ways that we look at the sun. We look at it in various wavelengths to tease out various features. And then filaments and prominences are just areas where plasma is held aloft in kind of a long caterpillar-like thing. And those occasionally lift off the sun and give us CMEs, but not like the violent eruptions associated with flares. This is just an artist's conception. You can see the blob coming off of Earth or off the sun, heading towards Earth, impacting our magnetic field, breaking the field lines up front here. They reconnect in the magnetotail and accelerate particles, charged particles, towards the poles, which leads to the aurora. And depending on how strong the storm is, this auroral oval will expand and move equatorward in both hemispheres. The typical sequence of events for a space weather storm starts with an X-ray flare. That gets here. It's actually already happened. It happened 8 minutes ago by the time we detect it, because we're detecting it at the speed of light, and the light travel time from the sun is about 8 minutes. You can have radio emissions that also occur. And then the next thing we have to look for are protons. And if we come up with model indications that suggest there could be a proton event, we'll issue a warning and then an alert. So sometimes we get minutes to hours of lead time on this, lead time being the time between when we issued the warning and when it actually crosses the threshold. The more we can give the astronauts, the better. This is going to become particularly important on the moon because there's no magnetic field to protect them. Then we look for evidence of a coronal mass ejection using that artificial eclipse I talked about earlier. If we think one's coming to Earth, we'll issue a storm watch, and we got an upgraded watch out for this event that just happened, which allows people to prepare. And for most people on the ground, normal humans, we're not going to have to do anything. But the power companies need to take measures to mitigate the impacts because it'll impose current on the power lines that's not supposed to be there, and that can stress the grid. So they need to find places to put that excess energy so it doesn't harm anything. Geomagnetic storms can also tear up the ionosphere, and that will impact GPS. And as many of you know, it will also impact HF comms. And then finally, once the blob is here, we'll issue a warning when we see it pass that satellite 1,000,000 miles out, either ACE or Discover. And then when we start crossing thresholds, that's when we issue the alerts. Now, right now, the coronagraph imagery that we absolutely have to model these things can be delayed up to 17 hours because they have to compete on the deep space network with other NASA missions. So we are getting our own coronagraphs at NOAA that will ride on the NOAA satellites, the GOES satellites to begin with, and then later another satellite parked 1,000,000 miles away that's called the Space Weather Follow-On. And those dedicated coronagraphs, we won't have to wait for the imagery. Because if the CME, those can get here between 18 hours and 4 days. So if you're waiting up to 17 hours, you got about an hour before you're dealing with it. So that is not good. And so we're working hard to fix that. And this year, we're expecting the first of the coronagraphs to go up. So that'll be awesome. We forecast for 3 different things. We forecast solar flares, which can lead to radio blackouts on HF. Although this term these days, this was not coined 25 years ago, but it was applied to these X-ray flares about 25 years ago. And it's kind of a misnomer now because since then we've developed digital communication methods that even in some of the worst of these conditions, the signal can still get through. And specifically, if you're thinking about FT8 or some of those other unique modes, that's a good thing. Radiation storms, those impact, I talked about the astronauts. It can also impact satellites. You can get those protons and heavy ions burying themselves in the actual silicon and causing things like bit flips and single event upsets. So it's not great to be commanding a satellite while one of these is going on or launching one. For extremely strong storms, it can actually penetrate deep enough in our atmosphere to be a concern to aviation at very high altitudes. The higher the altitude and the higher the latitude, closer to the poles they are, the more vulnerable they are to some of this. But the key thing there is you'd have to be exposed for quite some time, and the primary effect you'd be looking at is an increased cancer risk. And so they do keep track for flight crews, for instance, in Europe, who make frequent polar route crossings. And then finally, the geomagnetic storms. We got the top version this week. This past week, we got up to G5, which is a planetary K-index of 9, which is as high as it goes. Usually have about 4 of those per solar cycle. We only had, we had 0 last solar cycle. And so far, this is our first one this cycle. We've had about 3 of these G4 storms, which are severe, but not at this level. This is just another picture of a coronal hole. This is a big one. So those high-speed streams, like I said, they can cause mild to moderate storms. And that's just another image of the coronal holes. And this was neat because we didn't really see these well until the Skylab era. Prior to that, we knew there were recurring geomagnetic storms every 27 days, but nobody knew why. They knew it was something to do with the sun. So they decided to call these M regions, and the M stood for mystery. All right. This is just another way that we look at the solar wind. Some of the parameters we look at, including the mag strength, density, speed, temperature, and here's the KP index. So this is just an example chart. I'm going to stop talking now just to see if anybody has questions.
All right. So does anybody in the room have questions for our presenter today? We have one from Larry. What you got, Larry?
3664 is just going out of sight, going around the bend. That means might be a chance for it to come up another 14 days or so. What are the odds?
Oh, is it coming back in 14 days?
Coming back around.
Yeah, that's actually there's a decent probability. As long as it doesn't blow itself out, and just release all of its energy as it travels across, because they will decay on the far side of the sun where we can't see them. But a lot of them, especially ones of this size, will persist. And even if this particular spot group doesn't persist, it will. That's what we call an active longitude. So we keep an eye on that longitude, and as it comes back around, we look for development along there because it's got a history now. And whether or not these persist, like I said, it's difficult to know. We used to have spacecraft position where we could see it, but that was a research mission, and its position was constantly changing. And eventually, we lost contact with one of the satellites, and the other satellite currently is not in a great position to see the far side. We do have some techniques where we use sound from the sun, believe it or not. It's called helioseismology, and we take that information and we can actually start to identify regions that are suspect for sunspot formation, but that is not always accurate. We're working on making it better, and it's the best we have right now, but eventually we will have other observatories out there that can watch things as they go around the back.
All right, other questions? Yes. Yeah, let's
about for many years as a ham, we were thinking in terms of the 11-year sunspot cycle. We become familiar with 11 positive, 11 negative, and which really makes it a 22-year cycle. And on one of your graphs, they didn't look real similar. And I was wondering if the new model is really 22-year cycle and how your modeling has shown predictability.
Well, you're right about the 22-year cycle, because you'll flip the poles, and then to get back to where you started, that takes 22 years. So we still think of it in terms of an 11-year cycle, at least in my line of work. But they attempts to model it both on the 11-year and 22-year timescales are still, I would say, in their infancy. They're not really well developed yet, and we're still learning. There are some missions up there right now, like the Parker Solar Probe and Solar Orbiter, that will hopefully help us gain some more insight into what's going on up there that will allow us to make better models of these things. But as it stands right now, we've got some ideas, and that one gentleman, Scott McIntosh, whose solar prediction I showed earlier, has some really interesting ideas about waves on the solar surface that can be tracked and used to at least forecast short-term active periods of sunspots. So I think that's a fair summation of where we are right now.
All right, Lewis.
How likely is another Carrington event? And in your opinion, how close do you think it could be?
Well, there's been one of the things that's happened, and I'll tell you what, this recent storm was a great example. So for the past 20 years, we've been working with the power industry and the airlines and the astronauts and a bunch of different sectors, navigation, everything, to help them be more resilient in the face of these things. And part of that effort has involved scientists trying to determine exactly what you just asked. What's the likelihood? The paper I'm most familiar with from a scientist named Pete Riley came up with a figure about 12% over the next decade. So I don't think it's not out of the question. People, this is always, one of the toughest questions for us, because, if we're honest about it, we can give you some estimates, but, I don't think anybody knows really for certain. the best we can do is give you some estimates based on what we've seen. So I feel like this storm might be the big one for my career, but I'm not going to rule out something bigger happening. But our job basically is to be ready for that. And in the course of that emphasis on understanding the threat, there was a space weather operations research and mitigation task force formed to study a whole bunch of different things, like what's the biggest flare that could happen? What's the biggest storm that could happen? Is Carrington the biggest? I mean, we use that as a benchmark, but were there worse ones? What's the biggest radio burst that can happen, and on what frequencies? Because the sun, when it emits radio energy, that can be on any frequency, including in 1967, it can be on a frequency used for the Ballistic Missile Early Warning System, or BMUS radars. And that's bad because if our radars suddenly go out, that's an indication in 1967 of a potential Soviet missile attack. So that's a big deal. And it happened. Luckily, there was someone in Cheyenne Mountain who was a meteorologist and thought this could be related to solar activity. And so we narrowly averted thermonuclear war. And that was a real incentive for the military to pay attention to this stuff, even more so than it had been. And I talked to a scientist who was on the other side of the Iron Curtain during that period, and he had come over to the United States. And he told me that similar things were happening over there during that time, but he said, you'll never find records of it. So anyhow, I think that, yeah, it's the threat's there.
All right. Other questions? Josh.
What all does that teach us? And when do we need to be worried about it peaking?
Okay, I didn't hear the first part of the question. I heard about when do we have to worry about it peaking? What was the
Yeah,
first
he was
part?
talking about the density chart.
Oh, the density chart. Okay. So that's yeah, that's the solar wind density. So really what we see when we see peaks, that is that varies in very short time scales. So you'll see peaks associated with those coronal holes as they come around. There's something called a stream interaction region, and it just basically, you've got fast wind pushing up against solar wind, and it kind of piles up particles in that region. And so you'll get higher density there. So you'll see a density jump when that comes by. Similarly, with the shock from the CME, as it plows out into interplanetary space, it gobbles up a lot of material that will cause a density jump when it comes through. Interestingly enough, when you get into the high-speed stream, that's fairly rarefied. You'll see the density drop way down, and that causes problems for our spacecraft because it needs those particles to determine the speed and temperature and other aspects. But we won't be looking for like a crescendo on a solar cycle kind of time scale.
All right.
All right.
I actually have one question for you, and it has more to do with his deep historical stuff. You know, climatologists and everything have found all kinds of interesting ways to infer what went on thousands of years ago. Are there any equivalencies in studying the sun and how it behaves, and ways for us to infer what might have happened based upon evidence still here on Earth?
Absolutely. Absolutely. There are certain atmospheric changes that occur that will actually show up in things like ice core samples and in trees. So some of the same types of ways that climatologists dig deeper into what has happened are used by space scientists as well to do the same thing. And so I'm familiar with a couple papers that have been published about that, trying to get a handle on how bad it could get as part of that whole effort for mitigation. However, I'm not familiar enough with them to tell you what conclusions they reached. And I think I can say with relative confidence that they're fairly new techniques. So I think in a large part, the jury's kind of still out. We're waiting to see if they gather more evidence and we can understand it better. But they are taking advantage of those same types of techniques, and there have been some interesting assessments of what might have happened, and how strong. For instance, they were looking at radiation events. I remember, what could the strongest radiation event be? Because that's a question they need to really understand better. If we're sending folks to Mars, for instance, they're going to be out there for quite some time. So, but unfortunately, I can't give you any specifics about like what the results were.
No, that's great. Yeah, I just in my mind, I think about, okay, we've got entities here that are billions of years old, and we're trying to infer patterns based upon 100 years of observation.
Yeah,
the statistical significance of our observations seems small.
Oh yeah, you're absolutely right. I mean, you think about how long we've had instruments in space. I mean, it's a sliver. It's not. It's it's just it's tiny. And so yeah, there's a lot to be learned, I think, from investigating the remnants of what has happened. And yeah, we're hoping to take full advantage of that as we learn more about how to do it.
Okay, thank you.
Mhm.
Other questions in the room here? All right. We knew this was going to come up, and our field day coordinator just asked it. Do you have a forecast for field day?
Well, I'll tell you what, let me tell you this. The best for longer term forecasts like that, your best friend is what's called recurrence. And that just means look at the date of field day when you're going to be out there. Then look at what happened 27 days before that. That's the starting point that we use when we make our longer term forecast. The longest one we make is, besides the solar cycle, which I don't make in the forecast office. Like I said, that's a big group of people. But in the forecast office every week, we make a 54-day forecast of the geomagnetic AP index, a planetary A index, which is like a daily index. And then we make a prediction of the F10.7 solar flux. And our starting point for all of that is always recurrence, because we don't have any models that go really much beyond 24 hours at this point. The only one that does so consistently and does it well is the WSA Enlil model. But like our ionospheric models are nowhere near able to do that yet.
All right. Well, thank you for that answer.
Okay.
So, Mike, you have your assignment.
All right. Well, I'm going to go ahead and continue on. I did want to take a break because I realize I'm talking like an auctioneer, but see, I threw all that extra stuff in about the event that just happened. So I want to make sure I get through to the slides, to the stuff you care about. Well, the other stuff you care about, which is what do you do with your radio? All right. Here we have the Aurora model. That was a real big popular thing during this last event. Now, we don't have the 3-day predictions anymore. I need to fix that. That was a test, but they're still evaluating whether it was reliable enough to use, to put out there for the public to rely on, because you don't want people making reservations to fly somewhere to see the Aurora and have a verification rate below 20%. All right. What can we do? Okay. The flares, that's increasing ionization in the ionosphere, particularly absorption in the D region. And that'll increase the lowest usable frequency. So you'll have to use something higher. The flares are classified as common, moderate, or extreme. So when I talk about an X flare, that's an extreme flare. They typically last around an hour. Some are shorter, some are longer. The great thing, though, is you have that suffering brought about by, okay, I'm getting this absorption. And depending on how strong the flare was, it could affect a lot of bands. But afterwards, you get this kind of jazzed up ionosphere. It's not absorbing anymore, but it's really pumped up. So it's going to really transmit your signal or refract it. So that's awesome. And you can take advantage of that. So while the flare's happening, go make a cup of coffee, take the dog outside, whatever, and then come back in and turn the radio back on, and you can sometimes make some really extraordinary contacts. Geomagnetic storms, they work from the other side, so they bring noise, as you probably have figured out, and decreasing the maximum usable frequency, because chemistry within the storm will actually kind of gobble up the ionosphere, so you don't have a lot to reflect off of. And those things can hang around for like 3 days, and they move around the globe. And the important part there is keep in mind that these are not global in nature. They don't cover the entire globe. There are patches. And so you may be in a lull sometime where you can't hear anything. Bands are dead, and you're like, what's going on? Don't lose hope, because that patch may roll over, and then you may find yourself back in an area where you can communicate. And those are hard to forecast. I mean, we do our best with the models, but those are tough. And then finally, the space radiation storms can cause absorption in the polar region that can last for days. And that has an impact on air traffic, because you can't fly over the poles if you can't communicate via HF to the ground in those regions. Now, we're not doing polar flights right now because of the war in Ukraine. So we're kind of back to the Soviet era routes. But if those open up again, that's going to be a consideration. Now, over time, they've developed satellite communications methods that they can use too. So most of the carriers now also carry some satellite capabilities. All right, there's our friend, the ionosphere. You get radiation into the ionosphere, and what happens depends on the initial energy and what's available to absorb it. And the atmospheric chemistry and the energies, that begins to define the different ionospheric layers. And there are production and loss mechanisms for the ions. And in some cases, the loss mechanisms win, in cases where you get the maximum usable frequency depletions, but in other cases, it goes the other direction. I had to put some formulas on here just because, what would a talk about space weather be without formulas? But there are two frequencies we need to worry about, the plasma frequency and the frequency of your transmission. And there's a relationship there. The important relationship is the higher the frequency, the deeper into the ionosphere it's going to penetrate till you get high enough where it'll actually go completely through the ionosphere, and you'll be talking to satellites. So the frequency is one part, the takeoff angle is the other. So how it grazes the ionosphere and gets refracted. And this is the relationship for the index of refraction that's associated with that. And the other key thing that I'm showing here is that the plasma frequency, the thing you need to be concerned about, is related to the number of electrons. So your electron density in the ionosphere will determine what the plasma frequency is. And similarly, you can use that density along with the takeoff angle to give you an idea of what frequency you can use to get your best propagation. And that's what a lot of the propagation models like BOA-CAP are based on, these kind of relationships. Here's some maximum usable frequency and lowest usable frequency. You can have periods where you have a sudden ionospheric disturbance or a solar flare that does this, pushes your lowest usable frequency up. And at the same time, you might have had a geomagnetic storm, just like today we had an X flare, but we just got done with the geomagnetic storm, and we're still seeing the impacts to the ionosphere. So you may have also a depression of the maximum usable frequency. So this is where you really get issues with trying to communicate. So hopefully they're short-lived, and you can see the flare is typically going to be short-lived and things will open up again. But that's something to keep in mind. This is our D-region absorption product. I showed you one example of that earlier. You're going to get the absorption from solar flares over the sunlit side of the Earth. The proton absorption is going to occur at the poles. This lasts for hours. This lasts for days. Actually, this lasts for minutes to hours, depending on the characteristics of the flare. During 2017, I want to do this again for this event that we had, or this last flare. We got pretty close. We didn't get a 9, but we got an 8.7 today. But I looked at the weak signal propagation reporter connections, and I looked at it for the globe. I didn't just confine myself to the sunlit side. So I looked at for the entire globe, and I looked at the number of connections on these various frequencies. And you can see how it gets slammed when you get the X flare. And then they recover. And then they get slammed again. And then they recover. Now, the interesting thing here, the one thing I wanted to point out was, in these cases, all these trends are upward, right? But particularly 14 megahertz and actually 7 megahertz too, which is interesting. But 14 megahertz, remember I told you, you get that little jazzed up ionosphere? Well, that's what's going on here. So that's why you're seeing more connections now. This is just a lot of information about the maximum usable frequency. I'm not going to go into too much detail here, just because I've eaten up a lot of time already. But you can see how it changes over time. And they do maximum usable frequency calculations for different distances. So depending on where you want to talk, it's going to give you a different maximum usable frequency. And it also shows you the height of the F2 layer, which is the one we rely on a lot. But it also the E layer. This was just some work I did to show some depressions in, again, the weak signal propagation reporter from geomagnetic storms and maximum usable frequency depletions. This is a chart that, or a set of charts actually, from a model called the whole atmosphere model. Ones that amateurs would be particularly interested in are the maximum usable frequency here and the departure from the normal. So this is, I believe, over 30 days, whether you're seeing an increase or decrease. All right, so we're getting to the end here. There are hints from Paul Harden, and this was from the QRP ARCI website. He did a talk at the 5 Days in May presentation out in Dayton. And if you're in a QSO and a major flare occurs, it doesn't, he says, take a break. Don't quit, leave it on, because you get that bounce at the end that you can take advantage of. So good DX contacts possible immediately following until sundown, because you've got, and you get better signal to noise ratio for QRP. So that's kind of nice. And this is especially true during solar maximum years because you get more flares. Yeah, only for the duration of the flare. So generally, unless you have a sequence of flares, and that can happen, but unless you have a sequence of big flares, you should be able to get back on. Yeah, our magnetic field gets very quiet following a strong geomagnetic storm, and it'll simmer down. But remember, your ionosphere is also taking a hit. But generally, you're getting some low noise levels on the lower bands, so that can be a positive aspect. And then another hint is just use the our KP index on the WWV broadcast, or from our website, which is spaceweather.gov. Because that is updated every 3 hours. So that gives you a closer to real-time idea of what's going on. If you look, we also produce an A index, but that A index is for yesterday, and it's an average of all the Ks over the period. So some final thoughts. Yeah, the flux indicates the level of ionization. So the bigger the number, the better. But this is propagation. Typically above 10 megahertz, doesn't usually affect 40 meters and below, because The muff seldom drops that low. So you can use the lower band, and I was all over the lower bands in the last solar minimum. That's where I lived. The K-index, I talked about that. So a little more information there. 30 meters is weird. But it was the first band I ever did QRP work on. And so it's caught between, some of the characteristics of 40 and some of the characteristics of 20. But I'll tell you what, I got some amazing gray line propagation out of 30 meters. Everything's different. And the biggest tip I have for you here is never let the reports of flares or storms scare you from getting on the air. Check things out. Throw out a CQ. You may be surprised. Don't be put off if you hear reports of things. You don't actually go listen, because so much of what we do is on a planetary scale. We don't do regional forecasts, and the ionosphere is very variable to very small scales. So you may find yourself in a just fine position where, otherwise people are talking about the apocalypse. There's a group called HAMSI. WWV's been broadcasting since 1957. It's including some new signals for radio amateurs to do some scientific investigation, which is pretty cool. Here's some resources, our webpage. There's radio wave propagation tutorial, information on effects on electromagnetic propagation from the Naval Postgraduate School, VOACAP for predictions, and some other websites here. I have my little disclaimer. I can't say that no one's endorsing these, or the DOC or National Weather Service, but they're ones I like to look at sometimes. All right, these were questions that came from another group, and I hung on to them just because I thought they were some good questions. We talked about this already. The region numbers that we assign, like how did it become 3664? Well, we started, and actually there's a leading one, so we're 13664 now, because we've gone through that many solar active regions, sunspot groups. But as those come around and start showing up on the left side, that's when we assign a number. Now, the important thing to remember is, because we don't know what happened on the backside, on the far side, when these come around, they get a new number. So even if 3664 remains a big old spot and comes back around on the left side 2 weeks from now, it's going to get a new number. It'll be old 3664, and it'll have some new number. And we usually try and make people aware of that, that, hey, this thing, but we don't carry that number until we can see all the way around. We're not going to trust that, a region might have decayed and a new region formed somewhat nearby. And so we want to make sure we track those like that. Once we get some things on the far side, we'll probably be able to do maybe continuous numbering. We'll see. Solar wind can cause, well, anything from huge geomagnetic storms to minor annoyances, make pigeons get lost. So if you're a pigeon racer, this is something you'll pay attention to. KP index, we saw a little bit about that. And auroral activity. In a big enough auroral storm, if you're underneath it, you can get radio absorption. All right, that's it. I'm ready for any other questions you have. Thank you for your time. I hope I didn't burn up too much of it. I wasn't keeping track, but there's my telegraph key. So you're talking about CW operators. I'm one of those. I have so far thousands of those, and I think 18 SSB contacts in my whole life. So there you go.
You should come to this for field day. We'd love to have you. All right. Any further questions for our presenter? There's no questions in the room, Rob. It was very thorough. Thank you so much.
You're very welcome. And if any of you ever find yourself up here in Boulder, Colorado, I know sometimes people come up here because we got mountains and stuff, and it's awesome. But if you're up in this neck of the woods and you want to take a tour, hit me up. My email's right there. And I love to meet you guys. And I love to, I'm the only ham right now, active ham in the Space Weather Prediction Center. And you guys are just an amazing group of folks. And I like to keep my colleagues aware of all the neat stuff that you guys are doing. So
Very
thanks
cool.
again.
Thank you. Bye-bye.
Bye.
Good cartoon.